Let the acid and base react. This is not equilibrium. This is stoichiometry. Tell yourself stoichiometry. Chapter 4. Okay. And so we are going to take our weak acid, let it react with the strong base, not equilibrium. We form the conjugate base of the weak acid and water, which we could care less about, ICF. All right, so initially we still have our 25 millimoles of the acid. Now we're reacting with 24 millimoles of base. We don't have any of that there, and so we let the limiting react, decide the stoichiometry, and at the end we don't have any base left. We only have 1 millimole of the weak acid, and we have 24 of its conjugate base. So we still have our buffer. We still have just a little bit of that and a lot more of that, but it's still a buffer. So we are still going to be doing acid equilibrium. All right, step 2. Sorry, this is step 1. All right, step 2. We got to calculate the concentration of HA after the neutralization and how much salt we formed. Remember, this is our salt. And so we end up with 1 over 49, because we did 24 plus 25. And then we have 24 over 49. And that gives you your concentrations. So again, we're going to have 1 over 49. And that gives us the 0.020 molar. And then we have 24 over 49. And that gives me the 0.49 molar. All right. So that's pretty easy. Go up here to step 3 so that I can. I'm having trouble keeping out with a calculator on this one. Step 3. We're going to do we have our buffer with our weak acid and its conjugate base from the salt. So we set up our weak acid equilibrium. It's an equilibrium if you've got a buffer. All right, so this is a rice table because I added step 2 to your process. You already have the initial concentrations, 020 and 49. You don't have any of that. This is, of course, some will dissociate. Make, and at equilibrium, 0.020 minus x, and 0.49 plus x. But you know, Le Chatelier says if you have this present, it's going to dissociate less. And that's why we can always neglect the x as being added to an initial amount or subtracted from an initial amount. So again, we have that the H plus, since I've already done it, I don't have to write it for each thing. I can just bring it forward. It's going to be Ka times HA over A minus, right? And so that's going to equal 1.8 times 10 to the minus 5. That's the Ka for acetic acid. And the acid is now a lot smaller than the conjugate base. And that's a 9. Okay, and so we have that the hydrogen ion concentration then is, handy dandy calculator, we get 1.8, 10 to the negative 5. Please use your EE button right here for scientific notation. That's how I get it to put the little E there. Don't do the times 10. Waste of your time. 1.8 EE, that's made for scientific notation, just FYI. Then I'll plug in my exponent. Oh, I already did that part. All right, times 0.02 divided by 0.49, and that gives me 7.3 times 10 to the minus 1, 2, 3, 4, 5, 6, 7. Okay, and then the pH, because this is the hydrogen ion concentration. pH is the negative log of that. So negative log base 10 of the answer, 6.13. And that goes in your chart for 24. So you see it's a much more gradual, it's not that steep, sharp turn that we had in the strong acid, strong base. Once you have a weak acid or a weak base as part of your titration, your equivalence point is going to be much less dramatic. It's more gradual.